Evet. Okay, guys. So let's start our discussion. Now, I want to start with a quick review of a general control system, something that we actually are very familiar with, right? We usually talk about a feedback system, an output feedback system, in the sense that the system G of S is actually generates an output, and this output is measured by possibly another transfer function, a feedback transfer function H of S, the output of which is a representation of somehow the output, and this becomes compatible with the reference input. Okay, so we have this reference signal R of t, the output of the system, and basically the input to the system becomes what we call an error signal. Okay, so this is our usual single input, single output feedback control system. Now I want to really elaborate on this in order to reiterate some of the concepts that we have discussed. Okay, so I want to make this block diagram, which is the simplest feedback control system or feedback system, by simply illustrating some more detail about what can be involved in G of S and H of S and so on. Okay, so let's start with the reference signal R of t. Okay, so this is sometimes called a set point. It can be called a reference input, or it can be also called a desired value, provided that it's a constant, right? But we know that in general it can be a function of time. Okay, so this R of t somehow becomes converted, and this is done by simply passing it through a transfer function Gi of S, and what is in here is some kind of a transducer. Everything inside is essentially reference input elements. For example, a potentiometer that converts your angular setting into an electrical value is basically an input, reference input element. It's a transducer. It transforms an angular input into an electrical input. Now, at this point, the reference becomes compatible with what we have from the output. Okay, and usually the output comes through a function ht of t, ht of s in the S domain. So this again is some kind of a measurement transducer. Measurements transducer. For example, if it is again an angular variable that we are measuring, it can be a potentiometer. In fact, potentiometer is very widely used. If you have ever worked with these radio control servo motors, small black boxes, these are actually control devices. Inside there is a gearhead motor, so motor and gear, but there is also a measurement transducer, a potentiometer, which effectively measures the angular position. And there is also inside an electrical circuit which is basically an analog feedback controller. Okay, so what happens is that this servo device is able to control the angle based on the reference signal that you supply to it. So feedback elements. So this block consists of everything that is used to convert somehow the outputs into something that is compatible with the converted version of the input. Okay, so if you see here, there is the comparator device, which is the subtraction here. Remember, in order for variables to be subtracted here, they need to be of the same physical representation. If one is a voltage, the other one needs to be a voltage. If one is a let's say a position mechanical variable, the other needs to be a mechanical variable, right? They need to be of the same physical representation. Apples and apples, right? You cannot subtract or add things that are of different nature. So what happens is that here we have E of t, which we call the error signal. The error goes through a block which we call the controller. So a controller is a system that transforms the result of the comparison, often an error signal, into something called an actuation signal, actuator signal. Okay? Let's call this A of t. This A of t goes through the actuator model. What is an actuator? Well, we discussed it the last time. An actuator, for example, can be an electric motor. It can be a valve. It can be, I don't know. It can be anything that actually physically drives the plant or the system. Okay, so we can call this the actuator model. And this actually, the output of this is U of t, that we call the input. Input to what? Input to the plant. Okay, so finally we have GP of S. This we call the plant model or the process model, right? Now here we often include another signal which we will call the disturbance signal, D of t, the disturbance. Okay. In fact, a disturbance signal can be present anywhere in the system. This particular location is pretty common. It's called the output disturbance. That means what I measure as the output is basically a noisy version of what the actual output of the plant is. Okay, so this final variable I will call C of t. Remember, this is D of t. Now C of t is this signal, which is often called, now let me write it here, the controlled variable. Or simply the output. Okay. Now what happens here is that this signal actually is what we actually take out and measure by passing through the transducer model. Okay. Remember, this HT of S is sometimes also called the sensor model. Okay. All right. sorry, just went away. Now, which parts in this model actually require an in-depth knowledge of the physical systems that we are trying to model? How or which blocks in this model require the physical system knowledge? That means application knowledge about the system involved. What do you think?
Actuator, maybe.
Which one?
Actuator.
I couldn't hear you. It just was garbled a bit. Which block did you mention?
I wrote it on the chat.
You wrote on the chat. Okay, let me see. The actuator. Okay, so GA of S model, right? That's correct. Unless it is you who supply the actuator. Okay, sometimes the actuator may not be given. You as the control engineer may be the one responsible to introduce an actuator. That might be, let's say, your selection. But it is true, even if you select the actuator, you need to have an understanding of the physical system in order to design an actuator, right? What else?
Plant.
The plant, obviously, right? We need to have an understanding of the plant in order to develop GP of S, right? So this GP of S needs an in-depth understanding of what's going on. If it's a chemical plant, it is about chemistry, right? If it's an electrical circuit, you need to be able to analyze the circuit. If it's an electromechanical system, you need to analyze both the mechanical and the electrical part of the system. What else?
Sensor model.
Which one? Guys, can you also state your name so that I can know who's speaking?
Hocam, my name is Atakan.
Okay.
I said sensor model.
The sensor model, right? This over here, this transducer over there, obviously that depends on what kind of a system I have, what kind of output I have, and therefore how can I measure it, right? And so the same goes for the transducer at the input as well. We design the input elements often, okay? But still, we will need to know how to generate the reference signal that can be compared with the output, right? So if I kind of, let's say, so these blocks over here, right? The actuator, the plant, and the measurement device, right? These require essentially know-how in modeling the physical systems involved. So in order to generate these blocks and move to the mathematical domain, we need to apply our knowledge of physics, of mechanics, of electrics, electrical circuits, and depending on the type of the model, you may even wander into very different areas. In fact, we will see some examples, but in economics, in population control, you know, all of these areas would require domain knowledge in order to come up with the mathematical models. But once we have all the transfer functions here, all the blocks, then we are purely in the mathematical domain. Okay, for example, the design of the controller here, right? This block over here is a purely mathematical task. Okay, once you have the model, what the controller should be in order to have an desired output behavior is a completely a mathematical task. Okay. Any questions so far? I can barely hear you. Okay, go ahead. Sesiniz çok çok az geliyor. Bakayım acaba kulaklık falan. Söyleyin.
Ben mikrofonumu değiştireyim.
Yo, gayet iyi. Şimdi duyuyorum sizi.
Tamam. Hocam biz disturbance sinyali Plant'in output'uyla toplanıyor dedik ya.
Evet.
Peki bizim sensörümüzün ölçüp de error hesaplarken sensörümüzün ölçtüğü şey yine aynı disturbance'da mı lazım?
Şimdi şunu unutmayın. Bu bir model. Belli basitlikte bir model. Mesela ben şuraya bir yere de bir disturbance koyabilirdim. Mesela buna D1 disturbance diyelim. Buna D2 disturbance diyelim. Yani değişik yerlerde bu sisteme ben disturbance ekleyebilirim. Bu tamamen fiziksel prosesimde disturbance'ın, noise'in nerede geldiğine bağlı bir modelleme kararı. Yani değişik şeyler mümkün. Now, let me ask you a question. Now, once I add a disturbance signal here, is this still a single input, single output system?
Yes, it is.
Are you sure?
No.
I mean, if you have, let's say, a signal here that goes into the system, D1 of t, and you also have a reference signal here, okay? How many inputs do I have to this system?
Should be one. I think three.
Okay, now obviously if I also consider this D2, how many inputs do I have?
I still think it's one. Three.
Three inputs, right? This system no longer has a single input and single output. It still has single output, but as soon as you add a disturbance signal, this becomes a multi-input system. Okay? Now, is this a linear system? Is this a linear system?
Yes, because we are talking about transfer functions and we don't.
Very good, right? So we are talking about transfer functions. So in fact, transfer functions are defined for linear systems, right? So this is a linear time invariant system because each one of the blocks here are also independent of time. They are only a function of the Laplace variable s. Okay? So their parameters are constant. So it's a linear time invariant system. So if I have multiple inputs to a linear time invariant system, what do you have as a tool in order to analyze what's happening at the output?
I am again speaking. We can use superposition.
Very good, right? You can use superposition. What does superposition tells me? It tells me that if I make all the inputs 0, but only 1, and I calculate what's going to be the output in response to that particular input, and I make this input 0 and make the other input non-zero and calculate what's going to be the output, essentially making only one input non-zero at a time, the combined response at the output in response to all of the inputs being non-zero is basically the algebraic summation of all the individual outputs for each individual input, right? The linear system, the presence of a linear system with the property of superposition principle allows me to combine individual output responses to each one of the inputs at the output, okay? So in terms of circuit theory terminology, right, you kill a particular source, or you kill all sources except one, and you can calculate one by one the contributions to the output, okay? So let me kind of write this down.
Sesiniz biraz patlıyordu hocam. Ders başında söylemiştiniz, o yüzden hatırlatayım dedim.
Öyle mi? O zaman şöyle yapalım arkadaşlar. Bir saniye. Şuradan sese gidelim. Bir saniye. Şöyle bir şey de yapacağım.
Ders başındaki yazıya bir gelmek mümkün müydü hocam? Print screen alayım.
Şimdi geliyorum. Şimdi nasıl arkadaşlar ses?
Gayet bence. İyi hocam.
İyi değil mi? Çok azalmadı yani fazlaca. Tamam. Buyurun.
Birazcık daha üstte hocam. Tamam. Sağ olun.
Is there any questions at this point?
Benim bir tane vardı, sorabilir miyim?
Lütfen.
Ege bu arada benim ismim de. Şey soracaktım da, bir önceki örneğinizde yani o fiziksel olarak bir sistem yapmıştık ya.
Evet.
Oradaki plant şeydi değil mi hocam? O heating pipe'tı. Çünkü ısı olarak output istiyorduk. O heating pipe ısıtıyordu. Ama actuator'da plant'i drive eden şey de o dönme rotasyon hareketiyle valve'dı değil mi? O yüzden actuator dedik. Plant'in olmasına yol açtığı için.
Şimdi sınırı nerede çizeceğiniz size kalmış. Ama o örnekte temelde servo valve denilen ünite bir actuator olarak satılan bir şey. Servo valve nerede bitiyor? Sonuçta bir borunun üzerindeki bir açıklığı kontrol eden bir ünite bu. Dolayısıyla o ünitenin bittiği yer bir nevi o boruyu kapatıp açan pinin orada bitiyor aslında. Ondan sonra gerçekleşen her şey, işte o pinin sonucunda oluşan flow, o flow'un tanktaki suyu ısıtması vesaire, bunların hepsi aslında plant'in bir parçası kabul edilebilir. Now, let me elaborate on that. Think about it. I mean, in this block diagram, you can combine and separate many things, right? Remember, block diagram manipulation allows us to, for example, combine GC of S, GA of S, GP of S, and make them a single block, okay? You can do this in the mathematical domain. You can move blocks around. For example, I can take GP of S, I can take HT of S, and I can move it to the forward path. You can do many things, and you will still preserve the mathematical equivalence, okay? What you will lose is the correspondence with the physical system components, okay? Mathematically, you can do anything. You can combine, separate, move around, but this notation here is just to illustrate the correspondence with the physical system. And where you separate blocks really is up to you. As the control engineer, you give physical significance to mathematical parts of the model, okay? Therefore, for example, there can be a factor in the numerator of the actuator model. This factor can be moved to GP of S if you want to. It just as a different interpretation. Any other questions? Let me also ask you a question. Where is the controller? I mean, what is the controller in this block diagram? Okay, that's also an interesting question. Okay, so arkadaşlar birinizin mikrofonu açık ve arkasında bir takım sesler var. Onu kapatabilirsiniz. So obviously I call GC of S the controller, but controller is in fact it can include a number of things in a physical embodiment. Okay. For example, let me show you a way of interpreting it. Let's say this is my actuator G of S, GA of S. And let's consider that this is outside of the controller. Okay. And also let's say the measurement transfer function here, HT of S, is also over here. One way of defining the controller is anything beyond these transfer functions. So what's happening here is that the measurement is coming into, for example, especially in a discrete time control system, this signal goes through an analog to digital converter. Okay, so your reference signal comes in, R of t. This also goes, let's say, through an analog to digital converter. Inside of a computer, you make this comparison, you make this subtraction between a converted version of the reference and a converted version of the output. And you perform some calculations. Okay, so let me just make this a bit smaller. Okay. So let's say you have some calculations here inside a digital computer. Then you have a digital to analog converter. So you convert the result of these calculations into a physical analog signal, and you supply the signal, let's say an voltage, into the actuator. Okay. So where is the controller? Well, everything within this boundary, in this case, is the controller, right? And this controller, like this, is often inside a computer, basically. Okay, inside a, let's say, controller computer. Okay. Obviously, the presence of this analog to digital and digital to analog converter actually makes whatever happens inside this digital domain somewhat different from what's happening in the analog domain. Okay, so that this becomes essentially discrete time control in this case. Okay, unless you have all analog components that are implementing the controller transfer function, this whole thing becomes discrete time control. Any questions so far?
Hocam Özgür, benim bir sorum var.
Yes, go ahead.
Can we have analog controllers? Excuse me. Do we have analog controllers in real life?
Yes, we do. In fact, think about your almost the entire 302. Okay, like not the entire 302 because we have state space as well, but Think about root locus technique. Think about Route Horowitz criterion. All of these things were related with what we call the P control, or most of it was related with P control, right? A single gain parameter for the control. Correct?
Yeah.
Now you can implement this by an operational amplifier. An operational amplifier can easily implement a stable gain in an analog circuit, right? Now, this kind of control, for example, is often inside of your servo motors, those small servo motor devices that we use in our hobby projects, radio controlled devices and so on. These include an analog controller, essentially an operational amplifier gain. Okay?
In the industry, can we say like there's a percentage for usage of analog and digital controllers? I mean, is it like 20% analog and 80% digital? Can we say something like that?
Well, there used to be analog controllers like boxes that are supposed to control physical processes. But these are being transformed more and more into microcontroller based controllers. Okay, so it's becoming less and less. But in more particular applications, like for example, you have, let's say, an oscillator and an analog electronic circuit, and you want to obtain stable oscillations, then you might implement a gain-based and operational amplifier-based controller in order to obtain essentially uh, a, a controller for your circuit operation. Okay, there is a very very popular analog controller that is called a phase locked loop device. A phase locked loop device is often used in receivers, transmitters, and what it does is that you generate a, let's say, your oscillator generates a single signal in order to supply a multiplexer to decode a certain frequency signal. That oscillator needs to have a very stable frequency, and it needs to be locked to the frequency that you want to receive. Okay. In that case, a phase lock loop device is an analog controller to generate this kind of a very stable demultiplexing signal. So it is very popular, but it's not very visible. It's often buried inside some electronic circuits. It's often buried in very small devices. And more larger control applications, you see essentially the digital computer replacing any analog components. Okay. Now, what do you think is the biggest disadvantage of an analog controller?
It might be hard to implement.
Okay, it might be hard to implement. What else?
Again, we may not change it, we may not update it without completely changing.
Very good, right? And an update to the parameters of the controller requires that you redesign an analog circuit or essentially a device, right? You need to redesign a device in order to change the parameters of the controller. That's correct. What else? Can you speak a little bit louder?
Is it better now?
Okay, let me put on my earphone. Yes, I'm listening.
Okay, I'm Atakan. Maybe those analog circuits can be expensive because of mass production of microprocessors and digital electronics, and they can be digital more achievable.
That might be also an argument. That's correct. What else? There is a very important one, another one, Mustafa.
Memory.
Well, analog circuits don't have any memory, so memory is not a problem there.
Since they don't have memory, I thought maybe it may have a negative effect.
You need to elaborate on that, I guess. Because, for example, if you think about a P-type controller, what kind of memory do you need? It's already an algebraic equation, right? It just amplifies, your error signal.
Yes.
Options, they might be more prone to environmental factors.
Can you elaborate on that?
For example, with temperature,
That's correct. That's correct, right? Analog components often are subject to environmental disturbances, right? Their parameters might change. If it's a amplifier, let's say its gain might be a function of temperature, which means as temperature changes, your controller will be different basically. Okay? Arkadaşlar bir şey soracağım. Sesim hala arada patlıyor mu?
Evet hocam ya patlıyor maalesef.
Biraz daha kıssak çok mu azalacak ses?
Yok bence sorun yok kısa.
Biraz daha kıstım. Şimdi nasıl? Patlama azaldı mı? Hala bir cızırtı var. Bu cızırtının sebebini bilemiyorum. Sesim geliyor mu?
Kendi mikrofon değil değil mi? Harici bir mikrofon kullanıyorum.
Bu şu anda bilgisayarın mikrofonunu kullanıyorum. Geçen hafta web kameranın mikrofonunu kullanıyordum. Tamamen gitti.
Tamamen gitti, evet.
Tamamen gitti. Şimdi nasıl?
Hala yok.
Tamam bir saniye. Şimdi sesim nasıl geliyor arkadaşlar?
Şimdi de birazcık kısık ama.
Tamam bir saniye şimdi açacağım.
Şu an iyi.
Tamam. Bu yalnız şöyle bir sıkıntısı var. Bu kendisi ayarlıyor bu sesi. Acaba ben bunu manuel hale getirebilir miyim? Bir saniye. Audio settings. Evet. Şimdi sesim nasıl geliyor?
Şöyle güzel gibi ama
Şimdi nasıl geliyor? Çok fazla oldu.
biraz fazla oldu. Evet.
Şimdi iyi mi? İyi gibi. Tamam okey. Şimdi manuel yaptık. Sanıyorum otomatik. Şöyle bir kontrol sistemi sebebiyle sıkıntı yaşıyorduk. Çünkü otomatik gain control denilen algoritma bir süre sessiz kaldığınızda mikrofonu çok açıyor. Konuşmaya başlayınca da aniden kısıyor. Ve böylece kötü tasarlanmış bir kontrol sisteminin Peki bir saniye arkadaşlar. Tekrar sunuşumuza geçelim. Okay.
Hocam mümkünse kayda giden sesin de bu mikrofondan olduğuna emin olabiliyor muyuz?
Kayda giden çok güzel bir nokta. Hemen bakalım. Aslında kayda giden mikrofonu ayrıca seçmiştim. Fakat Zoom mikrofonunu seçmeyi unutmuşum. O yüzden o default'ta kalmış.
Tamam öyle.
Yani dolayısıyla kayıttaki sesin daha iyi olmasını bekliyorum. Ama ders arasında bir tekrar kontrol edeceğim. Alright. So that's kind of somewhat a review. Okay. Now I want to go back to what we called system identification. Okay. By the way, I cannot go back to the default color that I had when I started. So, okay, let's go with this color. So, system identification. So, what is system identification? System identification is where you already have a model Okay? System identification is where you, for example, from physical first principles, you have already derived a mathematical model, but unfortunately you cannot obtain or you do not know some of the parameters. System identification is where you combine the mathematical model that you have with some experimentation in order to obtain the parameters, the unknown parameters of the model. Let me write that down for you. Okay. Okay, let's use this. For some selected excitations, what is an excitation? Is basically a selected reference input. Compare the output of the model with the output of the physical system. Minimize the error. Obviously, you need to define what kind of error you have, because you have two signals essentially. So it may be defined over some measurements on the signal, or it can be defined as an integral of the error between the two signals. Minimize the error by tuning the model. What does it mean to tune the model? That means you just adjust the parameters. In some cases, simply by making measurements of the actual system response, you can directly determine some of the parameters of the model. I will show you an example after the break, but often this may become an iterative optimization process. That means you may need to have a computer to do that. Excite the system with different inputs, try to change, or with the same input, but try to play around with the unknown parameters in what we call an optimization process in order to make the model response closer and closer to the physical response. Let me sketch something that is a representation of that. You basically have a given signal, an input. You give this to the model, and you give this to the physical system simultaneously. You compare. So what happens is that you make a comparison between them, and the resulting signal, you basically bring it down to the model. This notation signifies that here what is happening is that you are adjusting, you're adjusting the model. Okay? Here the model becomes adapted to the physical system. Okay? So in system identification, you need to already have a model, and you conduct experiments with some selected inputs. You compare the output of the mathematical model for the same signal versus the response of the physical system for the same input signal. And the difference, you use it in order to adjust the model parameters. You try to minimize this signal E of t so that the mathematical model and the physical system, essentially generates the same response. In that case, you have an accurate model that you obtain through system identification. Okay. Now, there might be sometimes an additional step of more experiments, and that is called model validation. In model validation, what you effectively do is more experiments. Okay? Perform additional experiments to measure model accuracy. One question might be, is this really a separate step? Because I can always combine these additional experiments. I can move them to the system identification to get a better model. But the distinction in model validation is that your task is not to improve at this point the model. It's just that you want to measure what's the final accuracy. So you need to have some independent amount of data, let's say additional experiments, in order to make an independent measurement of the resulting accuracy. Okay. Anyway, these are some terminology that you will hear. Okay, you will hear system identification, and separately you will hear model validation. So you need to be aware of these different concepts. Okay. Now I want to make a note here about mathematical models, and we have already kind of discussed this to some extent. Even if you have a unique physical system, remember that a physical system may also change with time, and it may change with environmental factors and so on. But even if you have a system which does not change, which is fixed, which is unique, okay, this can still lead to many different mathematical models. Many different mathematical models. Why is that the case? Where that depends on the chosen complexity, which means you may wish to simplify the model by making some assumptions, and that's going to have a resulting accuracy. Okay, so you can have more complicated models, or you can have simpler models, depending on what serves your purposes at that point. Okay. A typical example is an amplifier, right? An amplifier can have a model that is a simple gain, just a constant factor, which is the idealized amplifier model. But in reality, an amplifier is implemented by a number of transistors. It can have dynamics in the sense that it can have a response time. So it can have, it can be a static model, just a gain. It can be a first order model, like basically a single pole, or it can have a much more complicated model depending on where you use it. There is a corresponding definition. When you have a model has a domain of validity. Okay? A domain of validity. Basically, this is an operational range within which the model is accurate enough. Okay? an operational range where means within which the model behavior accurately reflects physical system behavior. Okay. Okay, so let's have a 10-minute break. It's 10:35 at my clock. So let's meet here after 10 minutes to continue this discussion, okay?
Hocam, I am Özgür, by the way. I have a little question.
Yes, go ahead.
In the red model, what happens to the error signal? Does it go back to the physical system?
Okay.
The errors.
You mean the original feedback system?
No.
Okay, over here. Yes. This error signal is a different error signal, okay?
Yes, this is just calculating the accuracy, I guess.
Yes, that's correct.
What happens to this signal? Do we give it back to the physical system?
No, that's that arrow over there is not an actual mathematical addition or subtraction or anything like that. Right? This illustration here simply means that we are adjusting the model, okay? We are
Okay.
adjusting the model parameters.
Until the error is small enough, I guess.
Yes, that's correct. And how you adjust the mathematical model parameters is kind of depends on what kind of process you are using. For example, you can use an optimization algorithm that which gradually changes the model parameters and in an iterative way measures what's happening with the difference between the physical system response and the model response. Okay?
Got it, thank you.
But it can also mean that I am just calculating in closed form what the model parameters should be. And that's going to be our examples after the break. Okay? Peki. Ara verelim arkadaşlar. 10 dakika sonra görüşmek üzere. 47 geçe buluşuruz.